Hey everyone, thanks for coming. I'm super excited to introduce one of my favorite digital native customers, Ibotta. Just to give a little context here, they've done a really a fantastic migration from a cloud data warehouse and a data lake to Databricks Lakehouse. And Jaylyn and Manasa are going to go into a little more technical detail than I've seen in other talks here on tactics that they've used to optimize cost once they've done that jump. So if you're looking at how to improve your TCO on Databricks, this is a great talk for you from a technical point of view. I'll hand it over to Jaylyn and Manasa. Thank you.
All right. Hi, everybody. I'm Jaylyn. I'm a staff data engineer at Ibotta. This is Manasa. She is a data architect at Ibotta. We are talking about reducing total cost of ownership, techniques that we can use in the Databricks Lakehouse to do that. So start with some obligatory introductions about Ibotta. So Ibotta is a technology company in the retail CPG space that partners with over 2,700 brands and retailers to give our customers cash back rewards when they shop. So this includes white label partners like Walmart and Dollar General, and probably some other brands that you're familiar with. So essentially, users view offers for their favorite brands, unlock them, kind of like clipping a coupon, do their shopping, and then they scan their receipts afterwards, and we give them cash back for it. So we have over 45 million registered users, and they produce a lot of data. As you can probably imagine, we use that data for internal and external reporting. We have some machine learning powered data products that we sell to clients. And then it's hard to resist development of those AI capabilities that we've heard so much about this week. So we're looking into that as well. And all of this is really great and does a lot for us, but it costs a lot. Data platforms, as you know, are quite expensive, and Ibotta is no exception. But we've been working on lower the total cost of ownership for a data platform. And we're going to talk about some techniques that we use to do that today. So there are four kind of cost centers that we think about at Ibotta related to our data platform. So the first two are storage footprint and compute resources. Those are pretty obvious. And then the other two are engineering overhead and compliance and governance, or risk profile. Those are a little bit more nebulous, but they're equally as important as the first two because they're just as capable of blowing your budget as having a big S3 bill or a DC2 bill. So we're going to talk about those together. The second two are harder to forecast, but again, equally as important and equally important to optimize. So there are some things that we can do to try to rein those in, and we're going to talk about those after we talk about the more obvious ones in storage and compute.
To bring you all up to the speed, this is the high-level architecture of our data platform, showing data producers, data transformation layer, and storage layer. Our major sources of data are RDS snapshot data, which has offers, campaigns, and other details, event data, which is user interaction on Ibotta platform, and third-party data providers, external data that is coming into our platform. For orchestration, we use Airflow. We use that to read our raw data from bronze layer and translate, flatten it, and write it into our silver tables in Parquet, Delta. And gold layer is the business critical tables that is used for external reporting. Purple data is our inside term for development data and non-business critical data sets. We use Unity as our metastore to manage metadata, and Spark, which makes the whole platform scalable, performant, and secure. We are completely on AWS cloud.
Cool. All right. So let's talk about ways that we can optimize our storage footprint. So this is going to be the most straightforward section of the talk, and probably the one that most of you are very familiar with, aside from compute. A lot of this is going to be centered around things that you are built straight into your cloud provider. So in our case, it's AWS, so we're going to be talking about S3 features quite a bit. But there's also a lot of things that are specific to the Lakehouse that we can use to optimize costs, and we're going to get into those as well. So let's start with setting reasonable retention periods. Again, this might seem kind of obvious, but let's say the quiet part out loud. You don't need to keep all of your data forever. So you can start to reduce your costs by simply just getting rid of unneeded data, which in our case was mostly historical snapshots that would never see the light of day again. So Delta Lake lets us safely delete those old partitions and undelete them later if we need them within a certain period of time, right? In order to figure out what we can safely delete, we spend a lot of time with stakeholders, with consumers and business folks, just asking, what is it that you're actually trying to accomplish with your data? And is that something that we can accomplish with the current state, or is this something where we need to keep the full record for auditability or compliance purposes in particular? And what kind of features are available with Delta Lake to allow us to do that? So can we use time travel? Can we maybe organize the layout of the data a little bit differently so that we can store historical data more cost effectively? Those are all things that you can look at when you're trying to optimize your storage footprint in historical data. So next we fine-tuned the pricing for the data that we had left after we had gone through all our business cases and decided what we needed to keep and what we could get rid of. So all major cloud providers have something called storage tiers, so hot, warm, and cold storage. And they're priced differently, mostly based on retrieval SLAs. So again, Ibotta is an AWS shop. So for examples, we'll be using the S3 pricing model. They have a frequent access tier or hot tier at 2.3 cents per gig per month, an infrequent access tier or warm tier at 1.25 cents, and archive or cold tiers at 0.4 cents or less. And then the model is similar in Azure and GCP. So what we did is we applied settings across our entire data lake to progressively move objects down this ladder progressively based on if they had been accessed within a certain period of time. S3 has a feature called intelligent tiering that does this for you. That's super nice. But you can also configure this manually if you want a little bit more control over it. And so after a few months, what we ended up with was the vast majority of our data lake was in the archive tier, where it costs basically nothing on a per object level to store it, right? It's very cheap to store, but it can still be accessed if you need to, just with a little bit longer retrieval times. So if you need it for disaster recovery or audit, that's still available to you. You might just have to wait a little bit longer to get it out of the data lake. So this cut our bill in half, again, with very little effort on our part. Basically nobody noticed, except for the accounting team. So super easy win there. So to summarize what we did here, we ended up with our tables looking something like this, where we have a combination of rolling retention periods, where we just get rid of data that we don't need anymore for auditing purposes or compliance or year-over-year analysis. And the stuff that we do keep is in that tiered structure so that we only have to pay full price for the things that we need ready access to. And everything else can kind of progressively move that down and get cheaper as it goes until eventually we can just get rid of it. So these are specific to cloud provider. So this isn't really something that you do with the Delta Lake. Next, we're going to talk about what you can do with Delta Lake to further optimize here. So at this point in the conference, or at this point in your Spark careers, hopefully you've heard of optimizing and Z-ordering, which are features of all major Lakehouse formats, including Delta Lake. Optimize just compacts files so that they land somewhere in the 250 megs area. And then Z-ordering applies a clever algorithm that groups like values into contiguous rows based on how you want to index it, for lack of a better word, so that you get better compression. So what we did on top of all the things that we've talked about so far is now we changed the layout of the data that we had left by using these commands. So we started by converting all of our Parquet tables into Delta tables, and then started optimizing and z-ordering after each build. So we ended up with tables that used to have thousands of files compacted down to a few hundred, or even less in some cases. So this is an example number, but I have seen this in real life with massive tables shrinking by as much as 25%. So that adds up when you're talking about terabytes or petabytes of data. So just to illustrate this a little bit more, I created a 1 gig-ish data set with randomized values in low, medium, and high cardinality columns. So as you can see at the top there, without any kind of optimization, it's 176 files and 1091 megs with no additional optimizations. Then I ran the optimize command without z-ordering, and it ended up with 5 files and 193.8 megs. So it actually got a little bit bigger without any kind of z-ordering. But that's still acceptable because now you have 5 files instead of 176. So it's better for your query performance, right? So then down at the bottom, I started compressing it and ordering it a few different ways so I could see if I could shave off a little bit of that footprint. So down at the bottom right, you have the high cardinality. It didn't help that much. You only get 0.2% savings on that. But as you start experimenting with other combinations of them, you can shave, like down here, it was 6.8% that we took off. So again, that doesn't seem like much when you're talking about 1 gig of data. But if you do this across tables that are hundreds of terabytes in size or petabyte in size, that adds up. Which brings me to my last problem, though. When you do this, you create many, many versions of the same table, right? And the trick, or the mechanism that Delta uses to give you really cool things like time travel and ACID transactions is that it creates different versions of the same table and then tells the Delta manifest to reference those files instead of the unoptimized ones, right? What this means is that you end up with a lot of previous versions hanging around unless you vacuum them. So this command is from an optimization or vacuum that I ran while I was prepping for this talk and looking for some examples. Deleted 1.4 million files in one go. And so that obviously, if you don't do this, it negates all the savings that you're getting from the optimizing and z-ordering that you're doing otherwise, or makes it even worse. So just do yourself a favor. It's a 1-line command, run vacuum regularly. Just a quick note on that as well. The time travel is really cool, but it is not meant to be an auditing it's not used for auditing purposes, right? It's an undo button, not a historical record. So if you need that historical record, best practice is to create a date partition table where historical data is still part of the current version so that you can safely run vacuum and still get all those goodies from optimizing and z-ordering. Cool. Let's talk about compute resources now. So to illustrate what we're going to talk about in this section, I'm going to tell you a little bedtime story about a problem that we have solved in the back half of the year. So we had this Airflow DAG that our old BI team, our central BI team had written that was responsible for building several hundred tables or a couple hundred tables every night, and it was all kind of bundled together to look something like this. For simplicity, we used the same compute configurations across all of these tables just because there was so much going on that it was difficult to fine-tune each one of them individually. So it worked, it finished every night, but the downside was that there was a ton of waste. And we didn't particularly know where the waste was coming from. So super expensive, number one, because we had all of these tables and they were not necessarily similar in nature or the way that they were being built, right? The second problem was that there was a lot of waste, but we didn't know where to find it because we didn't have the right observability tools. And the third was an unfortunate lack of runtime quality controls. So if an upstream table on this end of the DAG had bad data quality issues, as we know happens in complex systems sometimes, what would happen is that it would propagate all the way down to the very end of the DAG, where consumers would find it in their core reporting tables before we did. So that's a problem. The end result of that would be that they would alert us to it, we push out a fix, and we run this entire pipeline end to end because of the complexity of it. We don't know, we couldn't pinpoint exactly where that problem was coming from, so we just had to rerun the whole thing, which means that all of that compute is wasted, right? All those compute hours are gone. So let's talk about how we fix this. So our solution was to decouple our workloads and start adding observability features so we could get a better handle on it. So in this graph, we've got a sensor that makes sure that the source data that we're using for this build is up to date, ready to go. Here, we've got a couple different kind of validations where we've got a circuit breaker that halts the pipeline if it runs into certain critical quality issues. And then we've got warnings down at the bottom that'll just tell us, like, there's something a little off here. Maybe you should look into that. Then we've got our main build. And then at the end, we have additional validations that will tell us something, again, something looks a little bit off here. Maybe you can take a look at it during business hours and figure out if there's an actual issue or if it's valid behavior that happens to be anomalous. The deeper details of this pattern are a topic for another time, but I want to zoom in a little bit on the optimized main build part, because that's where we got most of our compute savings. So let's talk about what we did here. The first thing that we did was establish benchmarks for that optimized main build, that main build portion. So we started by just tagging our compute resources with things that we'd use to logically attribute cost. So at Ibotta, across the board, we tag for organizational attributes like the owning team and department, as well as service level attributes like the name of the job and the environment that it's running in for like debugging purposes. From here, we use handy little tools to establish where we're at and really get a handle on what jobs and what organizations are producing the most cost. So up there is a handy dandy little DBU calculator that Databricks gives you. It's nothing fancy, but it does work really well. And then down below is an AWS EC2 cost chart. Those numbers are not real, in case you couldn't tell from the 1, 2, 3, 4, 5, 6. But that should give you a sense of the tools are available for you to kind of dig in and identify specifically where your problem areas are. So then you can start working from there and establishing patterns with those smaller use cases, and then apply those fixes across the rest of your data ecosystem so that you're solving many problems with a small number of best practices. So with that in mind, over time, we experimented with different kinds of compute. Databricks has many, there are many options, and they're all really good at different things. So over time, we developed a decision tree that led to something like this. So browsing, dashboards, SQL-only operations, those are really good with SQL warehouses. That's their fastest option in terms of startup time and performance, especially with serverless SQL coming out. For scheduled jobs, we use job clusters, so DML operations, things that are really predictable, where we can give it a standard cluster config, and we can generally predict what it's going to do. Single node clusters we use for machine learning workloads, training models, that kind of stuff. Things where it makes more sense to keep everything in memory together and co-located rather than on a distributed processing library. And then the other ones, there's lots of different use cases. I won't go into each of them, but this is generally what we ended up with. So once we had this, and we had optimized our own pipelines, we created blueprints for the rest of our organization to do the same thing. So we built Airflow modules and a cluster library that Manasa is going to talk about a little bit, and abstracted most of the decision-making needs away from everyday data producers, so that the hard parts are on us to figure out, and we can just give them the tools that they need to moderate their own costs without intervention from data engineering. Next up is arguably the harder part, which is tuning your actual queries and jobs. So there's a mountain of different techniques that you can use to optimize Spark jobs. Again, I'm not going to go into them here. There's a whole conference about it. But what we found really is that teaching people the top-level mechanics of how Spark works and providing those resources so that they can learn to solve their own problems and tune their own jobs is really what gets you the most bang for your buck. So teaching people the basics like wide versus narrow transformations, what is actually happening, starting to think of it in terms of data is physically moving from one machine to another, thinking of it that way rather than some kind of abstract, amorphous, I have a Spark job, I have no idea what it's doing thing. People want to know that stuff, and once they understand it, they get pretty good at optimizing their jobs. So things like giving them, or teaching them to navigate the Spark UI, giving them reasonable defaults like inactivity timeouts, making sure that they have an easy way to always stay on the latest runtime version so they get all of the shiny new optimizations, teaching them about Photon, making that available to them. All of that is really valuable. With that said, at the end of the day, what we found is just guiding people to the right compute type is a lot more valuable in reducing cost than agonizing over the internals of what your query is doing. Just to wrap up here, this is a snippet of some of the optimizations that we did. So as you can see here, there were some instances where we were able to improve DBU savings by over 90%. And I am going to tell you right now, most of that was not from optimizing the queries themselves, it was just choosing the right compute type. One more thing to keep in mind here as well, there's a couple of numbers on there where we increased our runtime, but still saved a ton of money in DBUs. That's okay, right? We want to make sure that we're doing what's best for the business and not necessarily what looks best in your benchmarking. So if there's more value in getting a job done fast or throwing more resources at it, do that if it's better for the business. Just eat the cost. Cool. All right, I'm going to hand it off to Manasa.
Thank you, Jaylyn. As Jaylyn mentioned initially, when we are thinking about cost, storage and compute are the things that come to mind, but there are things that you are not aware of, like they don't come to you when you're talking about cost, but they're very important in overall reducing your cost and saving some money. So let's get into some details. So Databricks provides a range of capabilities that we leveraged and developed some self-serving enablement tooling for our developers. So for both producers and consumers, we want to make things easy so that they can spend more time in developing valuable data products. So the things that I'm going to mention here are infrastructure modules, Terraform modules, some utilities that we built, cluster libraries, DAG factory, and schema evolution support that we leverage from Delta Lake. Talking about Terraform. So we use Databricks provided Terraform resources and built our own version of reusable modules. And we use that to treat our infrastructure as code. With this, it gave us capability to track changes to our infrastructure, maintain a version history, audit our infrastructure, and also in case of an incident, we are able to roll back our changes faster. You don't have to go do brainstorming of what what caused this failure. So that saves you a lot of time. So all this is giving visibility into our infrastructure cost. So as Jaylyn mentioned, we are able to standardize tags, and we are able to make dashboards available per team, and also you can also drill in a little bit more on per job by tagging them correctly. So all this will save you overall cost if you spend a little time, invest a little time building the right modules. So give you one example, we built something called base configuration module, base configuration manager, which we use to deploy workspace. So we have about 8 workspaces. So we use that to abstract away all the configurations and policies that you need per workspace. So by reusing this configuration module, we are able to standardize how our workspaces look. So you don't have to do that every single time. And we also created an infrastructure repository for our Databricks resources so that analyst, whoever is using the resource, they can go submit a pull request. It goes through approval process, but still they're self-serving and collaborating on how the infrastructure looks for all the teams. That is first example. Second, as Jaylyn mentioned, we use a lot of Airflow in our infrastructure. You have looked at the DAG before, but after developing this DAG factory, this has made things simple for our analytics teams. So there are common practices when you're developing an Airflow DAG. You're sensing on some tables, you want to get alerted when something fails. There is a PagerDuty that you want to associate with, and you want to either call a job, SQL endpoint, or submit your job, or call a jar. So all this is put into a DAG factory, and that is being leveraged internally. So all this is built on top of Databricks Airflow operator. And by changing a few things in your configuration file, you're able to put together DAG in matter of like less than an hour. So that saves a lot of productivity downstream, and also it is standardizing the development practices so that you don't run into these massive DAGs. So that was one of the improvements that we did to our pipelines. The third example is automated schema evolution. So by changing our storage format to Delta, we are able to leverage this capability of automating your schema changes, and by setting auto merge to true, you are able to remove the manual effort from the pipeline. So we have, as I mentioned earlier, we have close to 200 events that are coming into our data lake, and every single time the producer changes, adds a column, or makes some compatible change, you still have to go make that change in your tables. So by setting this to, by making this automated, we are able to templatize the whole pipeline, so it will look same for all the events, and you don't have to worry about the rewriting the data every single time they add a column. So this is, if you're not using Delta, this is something that you should check out and use Delta Lake. Coming to the compliance and governance section, so you might have heard in multiple keynotes, governance is not an option, nice to have anymore. You need to be compliant, or you need to secure data better, otherwise you will run into all kinds of problems. One data breach incident will ruin it all. So let's talk about things that we are doing. Governance and compliance, thinking about the cost associated with them. So the 3 things that I'll talk about today that we did at Ibotta are streamlining our current access and deletion process. Most of you are aware, with CCPA, you have to have access and deletion capability into our lake, and you have to protect, we are using access-based controls to protect PI better. And third one is getting visibility into how data is being used. So let's dive in. This is our old deletion process. So big challenge of data lakes is there is no transaction support, or there is no support for record level deletions. So we had to build a system on our own. The custom process used to read the files, delete, and write it back to our S3 bucket. So this is time-consuming and a resource-intensive process. So all this, while we are doing deletions, nobody is able to use that data, and it's not a reliable or a consistent process. So by switching into, like I mentioned, this is another big win for us. By switching into Delta Lake, we are able to leverage the ACID transaction support, and also we are doing deletion in a more consistent manner. And while the deletions are happening, we can reliably use the data set downstream. So the whole deletion process is now faster, taking less resources, reading less files. So the whole process is optimized. The second thing that I'll mention while you're thinking about governance is Unity Catalog. You might have heard multiple times that having a warehouse, data lake is difficult to manage, administer permissions, or you are doing copies, multiple copies of data, you don't know where the data is. So switching into Lakehouse and using Unity Catalog on top of it, so it made the whole data lake secure, and you're able to define roles, permissions, and you're able to Terraform those, and you're able to have track record of who has access to what data. So by doing role-based access is a big win in terms of governance, and also able to manage metadata from a single place so that you can define tables or have access defined from a single point. In our organization, we divided teams into different domains. So this is separating out the data that you should not have access to. So at the same time, we are giving them access to all the data that they need, no more, no less. So by dividing into dev staging, we are able to separate out accidental deletions or accidental overwrites that you do to a different domain. So you need to, once that happens, you have to spend hours and hours rolling back the changes. So this separates out the role-based access. So you're only getting access to your domain data. You only have write access to maybe development data sets and not production. So you have service principal to push it to production. So that makes it whole secure, at the same time giving you auditability. By using dynamic views, we are able to do column level restrictions. So all your finance data is secure, all your personal information. If you don't need access to certain columns that have personal information, manage it using dynamic views. That is also makes it more secure and also very useful in audit purposes. So the other one that we are leveraging internally is the Delta share with other domains. So if you want to share some data across domains, we add it to an internal share where others get access to your data. The last one that I'll talk about is getting insights into our data sets. So previously, it was all figuring out who owns the data. So it is a guesswork on which team owns which tables. So catalog is the de facto of your data lake. So getting into Unity Catalog, we are able to leverage like I mentioned, having insight into our data set and figuring out correct metadata to that column plays a huge role in our development lifecycle. So you are able to see how the data is being changed from point A to point B, who owns this pipeline, and in case of an incident, who should be notified. So the whole change impact analysis is now in a matter of minutes. Previously, you had to go through all the Slack conversations, and you have to figure out who owns the data. So catalog saves 80% of the time. To give you an actual example, this is one of the fact table that we built. So it gives you visibility into what tables are feeding into that fact table and who is using it. Like it was announced in Keynote, this will we'll be able to figure out what models are built on top of it. So that is the next step we'll be leveraging. So that is exciting. And like I mentioned, you can easily figure out if it is a PI column or if it is a finance data set, is it being visible to non-finance teams or which people should not have access to. You can control it using governance policies. This gives you ability to go secure your data lake and avoid any data penalties that could happen. So yeah, these are some things that we did at Ibotta, and hopefully some of this is helpful to you. There are some good announcements that happened in Keynote. One is Lakehouse monitoring that we are looking forward to, and also adding intelligence to our Lakehouse. So looking forward to using these capabilities. I'll end it here. Thank you.
All right, thank you both. Love to see the cost savings you had, really impressive, and the use of UC for governance. So yeah, we have a bit of time, 5 minutes or so for questions.